And we are back with another episode of Raw Green, ladies and gentlemen. I am Francesco Lieto, joined by my co-host Emma Me. Emma, what's coming up on this very day?
Well, Francesco, we're about to head into 3 months of darkness and cold in the UK, so it's about time we start talking about solar, don't you think? Solar is, it's now the cheapest, it does cheer us up. It's the cheapest, it's the fastest, it's the quickest to deploy electricity that we have in the world today, and we're obviously very familiar with big black rectangular panels going up in farms, on car parks and on buildings all over the place. But is there another way?
Well, we're about to find out, because in this episode of Raw Green, we speak with Neil Spann, the CEO of Roll, the UK company reinventing solar with flexible films patterned with microscopic grooves. So instead of rigid panels, Roll literally prints power onto lightweight rolls that cut production costs, materials, and emissions. Neil, welcome and great to have you with us.
Great to be here and looking forward to the discussion.
It's great to see you, Neil. So we really want to understand what this product is. You've engineered solar panels at the sort of microscopic scale, haven't you? It's sort of micro grooves is what I see, printed on your website and things. Tell us, how do they actually work, and why is this a breakthrough for solar?
Yes, so I always think it's easier to show to begin with. I'll start with a show and tell. So this is just a tiny example of one of our modules that we've made here. And what I'm holding in my hands, which is basically the size of an A3 picture, there's over 300,000 of our microscopic solar cells in there. So that really sets the scene. So if we stand back a little bit, the world of solar is really making solar cells the same way that it has for 40 years, which is in layers of materials, forming a sandwich, as we call it, the sandwich approach. And it's tried and tested, but it has some significant limitations. And what we have done is taken that standard sandwich, we have rotated it through 90 degrees and shrunk it down to a 40th of a human hair, into these forms of microgrooves. And each one of those tiny microgrooves, which is about 1 micrometer wide, is able to produce electricity from the sun efficiently at low cost, and has some significant advantages versus others. So we've literally turned the solar cell on its head and come up with this unique approach.
So just to for in layman terms, okay, how can we describe these microgrooves as like mini tunnels where the light passes through and gets pumped up on steroids? What happens into these microgrooves?
Yeah, if you think of it as, I guess the simplest way I would describe it is if you know a corrugated roof or a corrugated piece of metal, and obviously you've got a valley, and then you've got a ridge, and then you've got a valley. So that's essentially the structure we're using, but we've shrank it down, as I say, microscopically. And we can maybe talk about how how that invention was come about in due course. So what we've got is these tiny little sort of valleys, which we call the microgrooves. And what we do is, instead of what everyone else does, is put their electrodes on the top and bottom and sandwich the absorber material in the middle. What we do is actually put our electrodes and the semiconductors onto the sides of these microstructures. And then what we do is we come along and print the solar absorber, the solar ink, into the channel. And at that point, we've created the solar cell. So basically what happens then is the light can come from the top and basically be absorbed by the solar absorber, and then the charges are collected on the sides of the microstructures and channeled off to be connected into the real world. And not only can the light get in the top, and we'll talk about this later, the light can also get in the bottom of the groove. So I'm holding it in my hand this way, which means that actually we can generate energy almost equally from both sides of our film. So, which is again extremely unique. So if you think of them as little channels, we're collecting charge in those channels from the sun and extracting them. And that one cell, that tiny little cell, can generate 1 volt of potential difference. So 1 micrometer Y can produce 1 volt. And then what we do is, if you imagine go back to my corrugated roof example, we put the grooves next to each other. And as we add the grooves along, essentially it's a bit like adding batteries in series. We're basically adding voltage. So it's a really, really, we are the only people in the world that are deploying this technology to make solar cells.
I think I get it, Neil. I think you're turning the ice cream sandwich on its side.
That's exactly what we're doing. Yes, exactly what we're doing.
And then packing in more ice cream sandwiches.
Than that.
Yes. That's
There's
a
always
great
a
analogy.
simpler way.
That's a great analogy. Yeah, exactly. That's what we're doing. That's exactly what we're doing. And there's so many benefits of doing this. I often get asked the question, well, why has no one thought of this before? And because no one had thought of it before. So it's really, really super innovative.
Well, you say no one thought of it before, but are there examples of this sort of thinking and innovation being used anywhere else in other industries?
There are. So what we've got is, and we start with a standard PET substrate, and the microstructures are embossed into a resin that sits on top of that plastic substrate. So the use of structured films is a well-known art in wider fields. So I'll give you 2 examples. You've probably got an LED in your office where you've got basically the light is spread, and that's used using a microstructured film to spread light. A second example would be where people use microstructure films to reduce drag in aerodynamics. So the use of microstructures, and the more simple structure that you would use for microstructures is a hologram. And indeed, the technology, the machines that are used to make our film are the same machines that can make the Visa Dove or the MasterCard symbol. So structured films have been around for a long time. A structured film that can produce low-cost energy, that's what we're bringing to market. So yeah, we're using well-known processes to make the structures, but then deploy them in a way that's never been done before.
So, and is it because of that capability of capturing light from the top and from the bottom that allows you to perform better in low lights shaded environment?
I'll answer those 2 different questions here, Francesco. So from a shading perspective, so what you've got, if you go back to standard silicon modules and other types of modules, you end up with the sandwiches, and they make quite big cells. So using Emma's analogy, you end up with a big ice cream sandwich. They're sort of 180 mils by 180. They're quite significantly sized. And if you damage that cell, you lose quite a big area, and you might lose the cells next to them. So a small amount of damage can equal a large amount of loss. Because our solar cells and each of our modules electrically, so our solar cells 1 micrometer, and each of our modules electrically are a couple of human hairs put together. So what that means is, where we have damage, the damage is very much localized to where you have the damage. So you can shade this by 5%, where my hand is, you lose 5%. You don't lose more than 5%. So the shading and damage effect, not just only in production, but also in the real world, dust and debris and shading and all those things, we're much less affected because we've just got smaller cells. In terms of light conditions, two things are going on. The shape of the microstructures are beneficial for capturing light. So in particular on things like vertical facing, flat facing, as opposed to the traditional angles. But also then it allows us to use materials that perform better in low light conditions. So there's a mixture of what we call our architecture, which is really what PowerRoll is. We've developed a new architecture, and the combination of really exciting materials allows us to have advanced performance features. And as you said, the 2-sided approach, that was actually a happy accident. I'm going to say that. We were testing our cells and said, I wonder what happens if we turn them upside down. And actually, the result was 92% as good as the top side of the cell. So,
wow.
And because the microstructure, has a gap at the bottom and a gap at the top, it just allows light to pass way through. So for certain applications, which we will come on to later, that really does have some very significant benefits in the real world. But sometimes accidents and innovation can come together. It's fair to say, but that was a happy day when we discovered that discovered that fact. Yeah,
that's the nice part of when you develop a new technology.
Yes.
We get that. I got a few questions around that. I'm curious to know about efficiency. What is your efficiency compared to a standard mono poly in the range of 18-20%? What is Power Roll?
Yeah, absolutely. So if we stand back a little bit, there's three main vectors in solar: cost, efficiency, and life. The golden triangle, as people refer to it. Our mission remains, our mission is to get solar onto any surface around the world and generate cheap electricity, was to drive down cost. So this fundamentally is a cost play, and we'll talk about that later. So we want to have the lowest cost of deployed solar and the widest range of services you can deploy it. From an efficiency perspective, we wanted to have a good efficiency. So we have achieved up to 16% in the microgroup solar. Now there's more to come there. That will come.
And just help us, Neil, compare that to traditional solar, because anyone that might be hearing 16% might think that's low, but I think traditional solar is 19 to 23.
I mean, solar's moved on a little bit now, so you're into the sort of low 20s for solar now. 22% is pretty standard for the heavy rigid silicon panels. So that 16% at the cell level is good, but actually, because our film is very uniquely costed in terms of able to produce very low cost and able to install at low cost, even at as low as 10% at a large scale, 10% is able to drive a cost of electricity which is 70% lower than the grid cost here in the UK. So yes, you want as much efficiency as you can get, but from our perspective, 2 points. One, it's really about cost of electricity, because that's really what we're trying to deliver here.
The LCOE.
LCOE.
That's what you want to have,
absolutely. Yeah. But also the ability to open up the building envelope. Because you really see solar on the sides of buildings these days. One, because it's really heavy, and two, because it doesn't look particularly attractive. So what we can do is build out the building envelope. So yes, our efficiency will be less than the silicon panels, which, quite frankly, have been in development for 40 years. So, that's a very mature technology. That efficiency journey will come, but we've got, a roadmap that can take us into the 20% in terms of ultimate efficiency. But the key point is, we don't need to have an economically viable product. And that's what's really exciting. We always start at Power with the view of changing the economic proposition for solar. But efficiency is important. You need to generate electricity, of course.
So, Neil, you mentioned that as a 3-point triangle then between the cost and the efficiency and life. Does that mean that you're taking a bit of a hit on the life and the durability of something like this? Because you mentioned,
very good point,
low cost and lightweight, and we start to think, maybe a bit flimsy, maybe not going to stand up to general sort of UV and outdoor hailstone conditions, lightning, whatever else.
Yes, it's a tough old world out there, it's fair to say, but actually, and we've had some of our film out for 2 years here at our pilot factory up in County Durham, which has got an interesting set of weather. Not as extreme as some places, but you get a lot of temperatures, and it survived well. And actually, the film itself is extremely robust, because the microstructures are tiny. They're 1 micron, and they're sat inside a layer of plastics to protect it from the elements, which actually really, really protects the solar cells significantly. So, we've driven over this in cars. We genuinely have shot bullet holes through it. And because of the microstructure, this is where the microstructures will benefit again. Yes, you're going to get a bit of damage. If I cut this in half, I'm going to lose some microstructures. But actually, you don't destroy the rest of the panel. So it's incredibly robust. The bending radius of this is extremely low. With some other types of semi-flex solar, you're not allowed to bend them over a certain amount, or you crack the cells. There's none of that cracking goes on. So in terms of robustness, extremely robust, very much compared to traditional silicon, which is extremely delicate in its orientation, and the amount of panels that get damaged on the way to sites or onto buildings is phenomenal. From a lifetime perspective, where we came back to, again, we're being a bit conservative here. This is an architecture that's never been brought to market before, so we are targeting around about a 15-year life. And at first, we thought maybe that'll be a limitation for building owners. But actually, as we've gone to market, customers are really comfortable with that for 2 reasons. One, because of the low-cost economics, and this is in the UK, which we know is not the sunniest place, as you said earlier. you can deploy this on your roof at our MVP, minimum viable level of performance, and get you return on capital within 4 years. You've got another 11 years to generate significant profits, and then in year 15 we come along and we put another layer on top, and we refresh the solar film. And that is quite an attractive proposition, because in a previous life we were installing solar panels 10-15 years ago. Efficiency is double what it is today, so technology
they're
moves
doing
on.
tons
So
of revamping now and
yeah,
repowering across countries.
so
actually,
that's where we are. The triangle for us has always been led by the cost factor with a good efficiency and good life. That's essentially how we drive ourselves. And they will always continue to improve. But because the economics are so good, we don't need to have to get 25-year life, and we don't have to get 25% efficiency to get a good return for users of this technology.
Let me ask you something, Neil. If we finish this call and I decide to prepare a business plan to do, I don't know, 500 kilowatts of building integrated project with using your technology, okay? Before we talk about the cost per kilowatt of Power Roll, what I'm interested to know are two factors that should go into every business plan. The very first one, it is the efficiency decay of Power Roll, and second, the operation and maintenance cost. What are those two figures, especially compared with the current more common mono polysilicon solar modules?
Yeah, so in terms of operating and maintenance cost, and again, we're coming out of our pilot and into heading towards larger commercialization. So clearly we're still developing some of these, but from an O&M perspective, because of the less amount of damage, still need to be cleaned. You've got to clean these to make sure that even if you're not losing all of the efficiency because you've got some bird debris or whatever you've got out there, then they need to be cleaned. So there's going to be an O&M cost, but it will be lower than we expect for traditional solar for sure. In terms of cost of installation, and this is one of the benefits, is one of the things we want to do is get rid of some of the heavy racking requirements that's needed for silicon. You take a silicon panel, it's probably 20 kilograms or per panel, 12 kilograms per meter squared, plus the racking system. There's so many rooftops out there and building surfaces where you just cannot put this, you can't take the weight. Roughly 1 in 4 commercial buildings are just not designed to take that amount of weight, and it's a huge market. We'll come on to that later. So not only is the panel low cost to produce and manufacture, it's low cost to install. So no racking, easy to handle. This weighs just under 1 kilogram and more like half a kilogram when we optimize it for the commercial market. So it's 20 times lighter. So you can pick up 20
That's
kilowatts.
fantastic.
You can literally grab 20 kilowatts in your arm, and to put that in context for people watching this, that's probably 4 to 5 times what you would have on a domestic roof. So you're not going to carry those under your arm. It's fair to say, if you've ever seen someone manhandling a solar panel, they're incredibly heavy and difficult to install.
Yeah.
This is the absolute opposite. You carry it to the roof, you roll it onto the roof, you adhere it directly to the surface, and then 2 wires get connected off to inverters. From that point on, it's pretty much the same. You're generating electricity, but the cost of installation is also low, and that's where you get the double benefit from that perspective. So we'll come on to costs and what we think that'll be at a 500 kilowatt system, but it is extremely low cost and simple to deploy, not only on buildings here in the UK, but when you go to off-grid applications, agri-tech, it's about being able to deploy something quickly. Yeah, absolutely.
Think about all those old farms, greenhouses that they cannot wear the weight of a pigeon on top of it, and you can arrive with that. What about the efficiency losses though? Can we factor in like a 1% a year, 1.5% a year, something like market benchmark?
Yeah, around 1% is that's what we're estimating now. In this next phase of our ongoing sort of development and scale up, there's a lot of testing now that we're doing, because we can make modules, we put them outdoors, we put them through the accelerated testing that you have to do for solar. So You stress it with heat, you stress it with temperature, you stress it with constant light. Because obviously you can't test this for 15 years, otherwise we'd all be very old and be waiting for a product to come to market. So the results of those tests will allow us to understand that degradation curve, more effectively. But it's not to say after 15 years the panel won't work. That's not what it's about. It'll work to a certain level, and at that point we'll top it up. And I think that's the curve. So around 1 and a bit % over those years. So you'd be losing, around about 20% of the day one efficiency by year 15. That's traditionally what you'll see on silicon. You'll have a warranty of up to 80% power generation after a certain number of years. It's kind of the industry standard. But for certain applications, 80% might still be fine. And that's one of these people think, oh, they're dead after 15 years. No. They just have reached a different level of performance. But this ability to come along and literally stick another layer on top is something we're excited. And I don't get too far off track here, but if you imagine a big solar farm that's coming out of its life in 5 or 10 or 15 years, wouldn't it be pretty cool to go along and wallpaper on the top of all those existing panels our film and relife the assets?
Love that.
Low cost.
Because you've got the infrastructure there to take the energy.
It's already there.
Yeah. It's a relifing without having to take the panels away necessarily and do something. It's a bit like re-wallpapering your house. Not that many people wallpaper these days. I think that's, but that's the principle. Always the principle.
Much, Laura Ashley. Yeah, it's. But that's fantastic. The application. I haven't thought about it.
Yeah. Let's just wrap up the physicality of the product. Neil, tell us a little bit about how you manufacture them, and particularly you mentioned a good lack of rare earth materials.
Yes.
And how does that then affect how you can manage the end of life as well?
Yeah. So our chief scientist, Dr. John Topping, the inventor of this technology, and a fellow northeasterner of England, as you can tell from my accent. His family home is literally 3 miles from where our pilot factory is here. His background was in food packaging, and he has licensed some technology into that. Nothing to do with Power, but that's all about using low-cost, high-speed equipment to produce. If you've ever been to a food packaging factory, the speeds they can produce stuff is crazy. These machines are running at up to 500 meters per minute of stuff going through them. And when John designed these micro grooves, they were specifically designed to be produced and manufactured using similar equipment, which is used in holographics, food packaging, and the printing industry. So to make our film, we have 4 simple process steps. So the very first one is that I mentioned before, it's called embossing, where a PET, there's a very thin layer of resin put on. We have a tool made which comes along and basically puts the pattern into that acrylic and cures it. The exact same process as step 1 of making a hologram or a light structure. The second is what I call the crisp packet step, where we're basically depositing the metals on the sides of those microstructures. And the machine we've got downstairs could make crisp packets, but we've repurposed it to make solar cells. So we pattern the sides of the microstructures with the metals and semiconductors that we need. We then that's all done roll to roll. The next step, roll to roll, is we print the ink using a process called slot die printing, which is a very, very well-known process to deposit the ink into the grooves. And then the last thing we do is a lamination step, and it's think of an office laminator for simplicity purposes. We come along and sandwich our film between 2 layers of plastic to protect it from the elements, and we're done. And what that means is we've eliminated process steps that others need, because we've reorientated on our none of our electrodes are required to be transparent. And everybody else has to have in the flexible PV world a transparent electrode on the top. The top layer of the ice cream sandwich, going back to your analogy, has to be transparent and conductive. And that requires the use of indium, which is a rare earth material, and it's super expensive. By turning things on the sides, we just don't need that. So we've got simple processes that are low cost to scale and don't require any rare earth materials and are high speed in their nature. So that allows us to drive the production cost down. Less steps, less capital. It's very low energy, so we don't go above about 130 degrees C. which is the complete opposite of today's traditional silicon panels, which are very high energy intensive. They're heated up to 1500 degrees to get the right crystallinity. They use a lot of labor, and they're very capital intensive. And we are literally the opposite. And our ambition is to build a gigafactory for our technology here in the UK, and then have multiple gigafactories around the world with partnerships and licensing. But we estimate a cost of a gigafactory using our production processes to be around about 50 million sterling, which is a fraction of what you would need.
A fraction
of a fraction to build a silicon factory.
Yeah.
I sat on the government solar task force, and we, how do we improve our energy security in the UK? In terms of, can we make things here, because we're importing all of our solar panels, or virtually all of our solar panels in. And the conclusion was we can't afford to build silicon factories, but maybe we can afford to build factories for the technologies of the future like we're doing. And we're delighted that Power was referenced in the UK government solar roadmap. So watch this space for that. So that's really, really clear ambition to do that. So sorry, I drifted into the wider piece there, Emma.
No, and I want to get into that, but just quickly, end of life, Neil.
Yeah, so end of life. So we would either come along and put another layer on top, or we'd have to take the adhesive off and remove the panel. Recycling is, all of the layers are potentially recyclable. With PET, it's metals. I mean, what we've got is a very, very complicated crisp packet. But we know that crisp packets are not the easiest things to recycle. So we are not, at this point, guaranteeing that everything's going to be fully recyclable, because just because you can doesn't mean you should. But if you think about carbon footprint, and something we haven't covered, the carbon footprint in one of these panels is less than a fifth of that of a silicon. So you'll get something like, over your lifetime, a 20 times carbon payback. And in the worst case scenario, this has to be incinerated, the carbon footprint is still way ahead of anything else out there. So yeah, end of life, there's some work going on, and in our next series we're going to start to investigate that a little bit further. But complex layers of plastic are not the easiest things to recycle, but we have an ambition that we can.
I tell you what, when I come across a startup that is focusing on recycling crisp packets, I'll send them your way.
Yes, exactly.
Someone's got to.
So yeah, indeed.
Well, look, what the angle you're tackling, the manufacturing part, it is incredibly important. The Chinese government had to tackle in the solar manufacturers in China, because it was a price war that actually the entire world benefited from that. Let's be honest, but it is notoriously known that starting a solar PV manufacturing, it is extremely capital intensive, and with incredibly thin, razor thin margins. So if you flip that model out, it remains a very good value proposition from any investors. And I mean, we have a representative here that can confirm that. But my question it is, setting up a manufacturing facility in UK can be challenging. There is a reason why across the EU, but also in UK, rare earth materials are not done. You don't have that. But when you have to start to work on environmental permits and bureaucracy and councils, it is something not easy. Is it going to be something complicated to set up a gigafactory here, or your scale-up plant? Are you looking at other countries?
Yeah,
Tell me a little bit more.
Yeah, great question. I mean, we're a UK company. The technology was developed here. We've proven it here. We'd like to scale it here. I think in terms of the factory itself, we don't need a very complicated. We need a box. About for that gigafactory, let's say about an 80,000 square foot box. So that's quite straightforward. Okay. We will need a power connection. But no, we're not using huge amounts of energy, but it's a factory, so we need a certain amount of energy. So that power connection,
powered by Power Roll.
Yeah. Well, it's exactly. Obviously, we'd have our film on the roof giving us some power. There's no doubt about it. And interestingly, where we are today in County Durham, one of the super connectors from the wind farm off Scotland is coming 100 yards from our factory, the output. So we're thinking that could be interesting to imagine a factory powered by wind energy making solar energy. There's something pretty cool about that. So and the equipment we need is known, so embossing and vacuum coating, all those machines are known, but they have lead times. So the actual establishment of the factory, we don't perceive that would be significant challenges in terms of doing that. Not easy, but but not significant. One of the challenges is access to capital, and Green Angel Ventures have been great supporters of Power Roll to date, as of our other investors. But access to capital in that scaling phase is tough market out there at the moment, no doubt about it. Certainly in, I guess, late Series A, Series B is what the industry would call that, and that is a tough market. So I think one of the limiting factors will be that access to capital, and the timing of that capital will certainly be a driver. And you mentioned internationalization, so very much, if you go back strategically, at the moment we've got a centralized model. 90% of over 90% of the wafers, cells, and modules are made in a particular geography. We don't think that's a very good thing. I think the world's worked out that that's not a very good thing from an energy security perspective, and we're starting to see countries now saying, no, we want to bring something more local. So our model is very much a decentralized model. So we would like to have factories around the world making solar film, our Power Roll solar film, close to market. So you're reducing transport, you're creating local jobs. We think that's the right model. So very much our model is to establish global partnerships to find partners who want to establish factories in different territories. So whether that be in Japan, whether that be in India. So we are very much focused on 2 or 3 core markets at the moment, Japan being one, because there's a huge push in Japan to have low-cost, lightweight solar powered by a very particular solar absorber called perovskites. We've done half an hour of this podcast without mentioning the P word, perovskites, which is always quite complicated for me to pronounce. And
I was going to ask you about it, Neil, but I didn't dare my pronunciation of it all of a sudden.
It's the emerging material in solar. It's the world is converging that perovskites are probably the next generation materials after silicon, either putting them with silicon for tandems or using them by themselves. So this is a perovskite module powered by our microgroove. So it's kind of like plus. But if you take Japan, they've come out and said, right, we want 20 gigawatts of perovskite solar modules by 2040. And we're going to basically support industry in Japan to create that infrastructure. So for us, that's extremely powerful because that's a market that is perfect for what we're doing. So we are exploring international strategic partnerships as we speak. It's not really right for me to mention any particular names, but if we look in Japan, if we look in India, and we look in Europe and US, are probably the 4 key areas outside the UK where there's a growing demand to build infrastructure back to make solar panels, and you want something with limited reliance on rare materials or zero, which is us, low capital, with available materials that you can source geographically, and with techniques that can be understood and deployed, and that's fundamentally what we're doing. So our ambition is to have a first factory here in UK, but if the funding and the support is stronger in other regions, we're going to have a flexible model as we run forward. There's just no doubt about it. But there's a big push in the market at the moment, and I think what's interesting for us is, because you might ask who are our competitors potentially at some point, which is a good question, is there are lots of other companies trying to do flexible perovskites. There are many around the world. We are the only company that's doing it using microgrooves, and we believe and we know that's a better solution. Now, that means that these companies who are our competitors could actually also become our partners in terms of utilizing our microgroove architecture, getting rid of ITO, which is the expensive layer, simplifying the process, simplifying the steps. So it's an interesting dynamic that we see ourselves in. So yes, our ambition is still here, to build the factory here, to act as the blueprint, but we are in parallel exploring other opportunities. And we've had good, strong government support to date here in the UK. But there's always more that can be done over time, and maybe we'll talk about that.
You do talk about something that it is incredibly fascinating, especially in any startup that has to work on hard tech, deep tech, whatever. Is IP protection. Mm-hmm. I mean, any startup I work with or talk with, they are incredibly protective of their IPs, their baby. I don't want to share any information. I mean, Emma, that applies to you too when you have to evaluate any technology. And you actually went the exact opposite. You're opening up to outsourcing. You're opening up even potentially to competition to do that. So why? How was? Were you always been like this open in sharing, or is it?
You know what Northerners are like, Francesco. Honestly, they're very generous.
Yes, yeah. Well, we're not that generous with our IP. It's fair to say. So no, we've obviously built an extremely strong patent portfolio. We've got 27 families, 140 patents granted around the world. It's extremely strong. That covers the what. So anybody can go onto the patent database and learn about microgrooves. Absolutely, it's in the public domain. But the know-how, how do we get the grooves the right size? How do we put those things on the sides? How do we get the ink in the groove? All those things are what we keep. That is the secret sauce that we keep in the drawer. But for us, if you stand back, we're Little Old Power Roll. There's 40 of us here in County Durham. Our speed and ability to scale this product globally would be a limiting factor. We've worked in, some of us in this company on the board, we've worked in a bigger company that we managed to grow and scale to about 5,000 people and 750 million of revenues here in the UK. So we understand scaling, but scaling globally is complex, and for a company like us, that's very, very difficult. So we've always had the view that we would scale the production and the deployment of this through strategic partnerships. What do we know about selling solar panels in Japan? Absolutely not much. What do we know about scaling business in India? Well, a little bit, because we used to have one, but actually, so there's companies that are better placed to do it. So our strategy has always been to partner with corporates who can have access to market, manufacturing competence, and bring the product to market at scale globally, because it will just take too long for us to do it. So that openness comes in creating those strategic partners. So we're not going to go out there and share everything to everybody. But when we find the right partners, we need to really be open and collaborative with them to scale. So it's about, to me, it's about scaling technology globally rapidly, and trying to do everything ourselves would just not be a recipe for success. It's something that would just be very challenging, Francesco. And that's why, so we're not out there telling everyone our secrets, but certainly for our strategic partners who we're working with, and some in Europe and Japan and others, it's about how can we bring this to market at pace, because the world, we need to get this product out there, and we need to get it out there quickly so we can start making a difference. And that's the trade-off. If you do this and try and do everything yourself, especially in deep hard tech, it's going to be really, really hard to do that unless you've got $1 billion sat behind you, which we haven't yet.
What has been harder for you, Neil, the technology or the commercialization?
I think the technology has been hard, because it's something you both said, is this is so unique. So our patents are very rarely challenged in terms of prior art, as we call it. And actually, we just filed some new ones reasonably recently, and the last patents that were cited against us were older patents. So that's brilliant. From a patentability perspective, being very different is great. From a developing technology, it's really horrible. Because when we hit a bump in the road, we can't just go to, there's lots of experts around the world who are working on solar, National Renewable Energy Lab in the US, TNO in Europe, and we work with all of those. But what we need, we're the only people doing microgrooves. Our chief scientist used to say there's more people being on the moon than working on microgrooves. That's probably not true now, because we've grown the company a little bit. But that's been a challenge, because we've had to take what everyone else is doing and apply it to what we're doing. Now we've done that, that puts us in an incredibly strong know-how position. So that was very, very challenging. And it took us longer to get the tech from TRL 1 or 2 to where it is today. Or it's taken us a longer than we had envisaged because of that. On the commercialization and funding, we've been successful to a degree in raising capital for the business, but it's increasingly becoming difficult and very much at the moment. VCs are quite risk averse, want to take very little technical risk, and a funding environment is extremely challenging. And I speak to other CEOs of deep tech type companies; they're finding very similar. In terms of the commercialization, it's interesting because we haven't got a lack of people who want this product. Every day, someone will either be in our office or coming to us saying, "When can I have this? Can I put it onto this? Can I put it onto that? Can I do this?" But the challenge with our commercialization is How do you go from sort of pilot, as we are now, with some initial deployed assets, out into large scale? And that's where the challenge is, and we're looking to address that challenge through the strategic partnerships. So as I said, you either fund it yourself, or you bring partners in to work with you to then scale it. So I think the challenge is much more now in the scale up and commercialization than in the tech. But to begin with, there was hard miles. I mean, we spent just a single groove. Remember, I told you how small these things were. So a singular groove to get it to be a solar cell took a very long time. And now we're working with millions of them routinely day to day and producing hundreds of millions of microgrooves every day in our pilot plant. But it was a heck of a journey. It's fair to say, but an exciting and really interesting one. It's what we're doing is just it's really, really cutting edge and really exciting. But with that comes challenge, because people perceive that as risk. Or if no one's ever done it before, how do I know this? How do I know this? And no one's ever done that before, and that's where you get that's where the funding challenge comes in somewhat.
Can you share some project examples?
Yes.
I would like to know one really good project and one really bad project, something that went bad.
So, I mean, interesting from a project perspective. I think we've done some initial trials, again funded through Innovate, which I think has been very supportive of us on our journey, Innovate UK here, where we were looking into how we get deployed into remote villages in rural parts of the Himalayas of India, as well as in parts of Zambia. A really, really interesting. The use case is great. You can see it making a difference, and I think it really does. It opens up the mindset. I think in terms of difficult projects, we've not had any that have been disastrous, but I tell you where we have had challenges in the past is because our product is still in its development phase, and people often ask for samples and demos, and this kind of test this, and often we find that because we're developing stuff on a pilot line, we're still optimizing things. It's not a fully finished product that's ready to be sold on Amazon. That's not what this product is. I think sometimes you can get a misalignment of expectations, especially with international partners, maybe with a language barrier. So I think we've had a couple of challenges where we've sent something and there was a bit of an expectation gap, and I would say that's where we've had the biggest. A couple of challenges where we thought we'd explain things really clearly, but clearly we hadn't, as to what it was and how it would function and what it would function on. So I think that's been good. But we've had really many positive projects. I think because we're cutting edge here, there's sometimes we'll buy a piece of equipment, we think it's going to do X and it doesn't, or it doesn't quite do what we want it to do, and we've had to re-engineer things. So that's where it can be quite challenging. But that's the nature of the beast every day. And our team, it's interesting. We've got a great team of people, and brilliant scientists and engineers and technicians, and who are working to bring this to market. But we get a bit blasé. It's like, oh yeah, we sorted that out. It's like you realize no one else has ever sorted that out before, and it's kind of we get used to the fact that we're breaking new ground every day. It's quite a weird. We'll beat ourselves up because we were late on something. It's like, yeah, but no one's ever done that before. And that's the counter. So. But we've got some really good projects coming. So this next phase of scale up for us is about. So we've got demos. Demos. So we've got some demos here at our factory, on the sides and on the tops and different angles. For example, you place this vertically because it's bifacial. If you imagine your energy curve during the day, if you put this in the right orientation, you get the sun on this side, you get the sun on this side. It can really broaden out so there's lots of innovative things we want to try.
East-west, rather than north-south,
exactly. So, but the next phase is we want to try and get that onto larger systems, onto our partner buildings. So we've got one lining up in Germany, one in Japan, to get it out there, because that's where this is it's going to live in the real world and be impacted by all sorts of things. So that's the exciting thing for us now. That's the next big set of projects for us, which is both exciting but also lots of challenges because we've never done it before. So that's the next phase.
Timeline wise, sorry Neil, this is important. Timeline wise, when can I buy a megawatt of Power Roll? What would be the ideal scenario? Say January 2027, or if you have a deadline in mind.
Yeah, no, absolutely. If we had the capital in the bank today to build the first factory, we would be targeting the middle of 2027 to be getting into production. We do not yet have that capital secured. So from securing capital, you're probably looking at about a 12 to 18 month period to get a factory up and running. You've got to order the equipment. You've got to go through all the processes and certification, etc. So it's difficult to be precise, but we want this as soon as possible. We are looking to raise capital to get us into that position at present and over the next wee while. So I would estimate right now probably at large scale 2028, and we're doing small scale projects before that, but that will very much depend on timing of capital. That's what's really going to be the driver now for us, Francesco, as we go through this next phase is access to that scale of capital, which would be able to then move on to larger scale production. And that's
this is energy security, Neil.
Yes,
sorry, but this is energy security. Wouldn't the government pitch in into something like this? If you have homemade UK manufactured solar panels or solar film in your case, wouldn't that be classified at energy security level? I mean, the whole narrative around ESG now has been reframed under energy security and governments. So it is, and it is. It isn't just a commercial or marketing thing.
No, absolutely. I mean, the alignment to government policy on creating green jobs, energy security, and deploying renewables is extremely strong. And as I said, we've had good support from government, and we continue that dialogue. So really, the question is one for government to answer, but very much this should be scaled, with government support and also private sector capital coming in. So it's always going to be a mixture, but for sure those conversations continue. And I can't say too much at this point, but we were delighted to be
not covered by AP.
No, but I'd be delighted. We're delighted that we were highlighted as the leading company in the UK from the government's recent solar roadmap. So yes, I think there is a strong desire to see a company like Powerwall build gigafactories here, because why wouldn't anybody want that? It's absolutely. But there's a lot of priorities, obviously, at present that the government's working on.
So Neil, just paint a vision for us as a bit of a final question. Where do you see the Powerwall film going in the future? What are the fun ideas that you've had about where you want to what you want to turn into a sort of a mobile power station all over the country,
all over
the
people
world?
with that and send them on the street to generate electricity?
What's the vision?
I like that one, Francesco. Well, the vision is that literally almost any surface you see. So the vision is, this is powering businesses. So the tops of factories, the sides of factories, you just see it. You're driving down the M1, you see all these massive sheds. They will have this film attached to them. That's all over the world. The second is deploying this into off-grid locations, because this could go on a tarpaulin, it can go on a sheet metal roof, it can go anywhere. So getting this into those rural communities that don't have electricity. Still 600 million people in the world without electricity. This is a way to get low-cost power to them. The third is powering agriculture, greenhouses, water pumping, smart agrivoltaics. So then you've got powering transport. So you've got putting this on trucks, on the sides of trucks and the tops of trucks, but also soundboards, carports. Imagine a carport where you need much less racking. So basically, the vision is everywhere, and then you get into some of the really sort of out there applications. So tensile structures, disaster relief onto sides of aeroplanes. This is put it into space, because there's an issue with space is all about weight and power. We've got a huge power to weight density. So this literally is almost wrap the Earth. If you wrap the Earth in solar film, that's the ultimate vision. But we're going to do it surface by surface. And we believe that we can use more of the surfaces to create energy. We don't need as much of the land to create the solar energy. And solar farms have a place, and everything's an and. But that's our vision. So if you're on a car, if you're on a plane, and you're in a train, and you look down, you're just going to see our solar film generating cheap energy. That's the ultimate vision. And we think we've got the underlying technology to make that happen.
Fantastic. Thank you, Neil. This was a phenomenal conversation. I mean, I am a cheerleader for anything regarding solar, so you got another cheerleader for Power Roll too. Thank you for being on Raw Green, and look forward catching up with you too.
Thank you.
Great to be here.
Ciao, guys. Thanks for listening to this episode of Raw Green. If you made it this far, you probably enjoyed it. So don't forget to hit subscribe and follow our podcast. It's an awesome way to support our community. At Obi, we're all about research, life cycle assessment, and green tech innovation. Stay in touch through our socials or visit our website. Links are ready for you in the description. Catch you in the next episode. Ciao.